All right, welcome back to officially the first lecture after spring break, kind of paired with week 9, day 3 that we never got to last time. Quiz 8 is due today. If you need an extension on that, make sure you let me know. Homework 24 is also due today. So, today we're going to be talking about the magnetic force between two wires and then an alternative to Biot-Savart law known as Ampere's law. But to start off with, we will look at the force between two parallel wires. And we're going to look at two different situations. One where we have current in opposite directions, and one where we have current in the same direction. So let me draw some example currents here. So for currents in the opposite direction, we might have current I1 traveling up and current I2 traveling down. And if we have currents in the same direction, we could say both of the currents are traveling up for the sake of our diagram. So I want you to kind of pause the video right here and see if you can figure out why two parallel wires should exert a force on each other. Hopefully you've done that and you can have some sort of general idea, because we know that a magnetic force will be exerted on a wire when you place that wire into a magnetic field. And that formula was IL cross B, where L is the length of the wire and has the same direction as the current. So if we want to know what direction of force each wire experiences, we need to know what magnetic field each wire is experiencing. So over here, when the currents are in opposite directions, looking at wire 1, to know what force wire 1 experiences, we need to think about what magnetic field wire 1 experiences. And since a wire, at least not yet, not till we talk about induction, since a wire can't feel its own magnetic field, that magnetic field must be coming from somewhere else. And it's coming from wire 2. So wire 2, based on our right-hand rule, second right-hand rule, will have a magnetic field into the board on the left side of the wire and out of the board on the left side of the wire. Which means wire 1 experiences a magnetic field into the board that I'm going to call B2 because it's caused by wire 2. And now we have a current pointing up experiences a magnetic field pointing into the page, leaves us with a force acting on wire 1 that I'll call F1 to the left. Now we can do the same process in reverse for wire 2. The magnetic field wire 2 experiences will be caused by wire 1. And wire 1 will create a magnetic field out of the board on the left side of wire 1 and into the board on the right side of wire 1 from right-hand rule number 2, which means wire 2 is experiencing a magnetic field into the board caused by wire 1. I'm calling that B1. So we can do our first right-hand rule and find that F2, the force on wire 2, acts to the right. So when current is in opposite directions, we get a repulsion between the wires. Now I recommend pausing the video here and seeing if you can work out what happens when the wires go in the same direction yourselves. So go ahead and do that. Welcome back. Let's check your answers here. So we go through the same process here. Right-hand rule number 2 says wire 2 creates a magnetic field out of the board on the left and into the board on the right. So wire 1 is experiencing a magnetic field that I will call B2 because it's caused by wire 2, acting out of the board. So now we know the direction of our current, up, and the direction of the magnetic field experienced by that current, out of the board. Then we can determine the direction of the force. And that force will be, in this case, to the right. When we go through the similar process for wire 2, well, wire 1 creates a magnetic field out of the board on the left, into the board on the right. So wire 2 experiences magnetic field B1 caused by wire 1 into the board. And then when we go through our first right-hand rule, we get wire 2 experiences a force to the left, or towards wire 1. So when the currents are in the same direction, we have an attraction between the wires. So this gives us the concepts of this process, but there's a little more to the math of all of it. So to figure out the math of all of this, I want to do an example. And for this example, I want to find the force between headphone wires. Now, for those of you youngins who only are familiar with AirPods and things like that, this is what a pair of headphones used to look like. You have the two headphones down there at the end, and we have a long section of wire where the wires for the two pieces run together, two side-by-side wires. And this is going to be the length of our wires that we're going to consider. Based on my own headphones, I calculate this length is about 40 centimeters. We're also going to need to know the separation between the two wires. And looking at my own headphones, it looks like the separation between them is about 2 millimeters. We're going to make an assumption here. We're going to assume the current in the two side-by-side wires is in opposite directions. And the value of that current, something I looked up online, it'll change over time, but on average it's around 25 milliamps in headphones. So we want to find the force between these two wires based on what we know about the magnetic force and the things that cause magnetic fields. So go ahead and give this a go and see if you can figure it out on your own first, and then use my work to check your own. The formula we're going to be using here is the magnetic force formula. We'll just work in terms of magnitudes for now. So we have ILB sine of theta. So now we need to figure out what some of these values are. Theta here is the angle between the direction of the current and the direction of the magnetic field. So if you look over at the diagrams on the left, hopefully you can convince yourself that theta is going to be 90 degrees. So sine of theta is going to be 1, and we can just ignore this part of our formula. Well, we have numbers for I and for L, but we're going to need to figure out what magnetic field to enter here, how to find the strength of the magnetic field. Well, this is the magnetic field from a long straight wire. Since it's these long straight wires creating the magnetic field that is being felt by the other wire. So we should check to make sure we can use this formula. This formula tells us we can only use it when the length of the wire is much longer than the distance of the test location from the wire itself. So if we are dealing with currents in the opposite direction, when wire 2 creates a magnetic field, it's going to create a magnetic field this distance r away from it. Here r is going to be 2 millimeters, and that is much smaller than 40 centimeters, so we absolutely can use our formula. B is mu naught I over 2 pi r, where r is going to be the separation between the wires. So, excuse me, plugging this all in, we can see that the magnetic force on one of the wires will be the current, which is 0.025 amps times the length, which is 0.4 meters, times the magnetic field from the long, straight other wire, which is mu naught, 4 pi times 10 to the negative 7th Tesla meter per amp, times the current, this time in the other wire, which is the same as we've assumed in this problem, divided by 2 pi times the separation, which is 2 millimeters or 0.002 meters. Over here in this term in brackets, this is all just the magnetic field. So you can see the Teslas will be left behind and the meters and amps will cancel. And then we'll be left with a Tesla meter times an amp, which is equivalent to a Newton for our force. So just rewriting this briefly. We do get 2.5 times 10 to the negative 6th Tesla, or microtesla if you prefer. And then we can find the force, which works out to be 2.5 times 10 to the negative 8th newtons. And since the currents are running in opposite directions, this is going to be a repulsive force. So left myself a little space down here in the left to, we'll use pink, to make a couple of notes. One of them is that Newton's third law applies here. What I mean by this is that the magnitude of F1 and F2 are the same, but they point in opposite directions. So we could write that mathematically as follows. Remember, multiplying a vector by a negative 1 just flips the direction to be opposite. Another thing that's worth mentioning is that you will often, instead of the force directly, calculate a quantity called the force per unit length, which is just F divided by L. So basically, how much force would a 1 meter section of this wire experience? And by looking at our formulas that we had from our example on the other side of the page here, you can come up with a formula that is mu naught times I1 times I2 divided by 2 pi r, where again r is the separation between these two wires. So note that whether you're finding the force on wire 1 or the force on wire 2, we have both of the currents involved. So you'll get mathematically the same magnitude of the force either way. So that's everything I plan to say about the force between two parallel wires. So I'm going to clear this off so that we can start to talk about Ampere's law. And Ampere's law is fundamentally a way to find formulas for the magnetic field that isn't Biot-Savart law. And first I'm just going to write the formula for Ampere's law, and then we are going to unpack that formula because it's going to be something very new that we haven't seen very much of before. We have an integral sign with this circle on it. Inside the integral, we have b dot dl, both vectors. And that will equal mu naught, our permeability of free space, times the enclosed current. In your book, they just call this I. I'm going to put the subscript ENCL on there, specifically to refer to it being the enclosed current. And we'll talk about what that is in a second. First, this integral symbol here. There's just one integral symbol, which means this is a line integral or an integral along some sort of one-dimensional path. It's not an area integral or a volume integral. But that circle right here means it is a closed integral, meaning we end the integral back where we started. So this part means we are taking the integral around a closed loop. So the loop we're talking about here is not an actual physical loop of wire or anything like that. It's an imaginary path we take through space. Think of the loop for Ampere's law a lot like the box from Gauss's law. It's just an imaginary space we draw in order to do our math. So we might have a loop that looks something like this. It's much harder to draw dotted lines on here than it is on the chalkboard. There we go. So this could be our loop that we would integrate around. And what do we want to add up? What are we going to find for each small chunk of this loop? We're going to find b dot dl, which is the dot product of B, our magnetic field, and dl, where dl is the path of the loop we follow. So as we go all the way around this loop down here, for each chunk of length, we will find b dot dl. Maybe we're dealing with this small chunk of the loop right now. This dl, small chunk of the total length of this loop. Then at this point, we would want to find the magnetic field at that location and take the angle between the two of those and use that to evaluate the dot product, this angle right here. So, and then maybe some other point on the loop, perhaps right here. It's usually convention to go counterclockwise around these loops, so that's what I'm sticking with. We would again find the magnetic field at that location, take the dot product of it with this tiny little length element, and then we would add up all of those pieces together for the entire loop. Note that the dot product can be positive or negative, so we're really working with here is trying to find something about the component of the magnetic field that is parallel to our path. So up here above, we would have a positive contribution. Since our magnetic field and our path of our loop are less than 90 degrees apart, so we would get a positive dot product. Down here, we would get a negative contribution to our integral because the angle between b and dl is more than 90 degrees. Last but not least, we have I enclosed, which is any current enclosed within the loop. So I'll give you an example here. So if we have current I1 coming out of the board right here, that is within the loop. If we have current I2 going into the board right here, that is also in the loop. But current I3 out here, again coming out of the board, is not enclosed within the loop. So we have I1 and I2 are enclosed, and I3 is not. So if we're trying to find I enclosed, we need to pay careful attention to currents that are going one way through this loop versus the other way through the loop. Usually you'll take out of the board as positive if you're working counterclockwise around the loop. So for this example, we would take a positive I1 and subtract I2 from that to get our enclosed current. We have a general procedure for Ampere's law. I'm going to show you this general procedure, and then we will do 2 examples with Ampere's law, and then that's all we're going to talk about today. So, the first step is to check the symmetry of the problem. If there's no good or easy symmetry, don't use Ampere's law. Use Biot-Savart law. Biot-Savart law is not always easy to evaluate, but it is a brute force mathematical approach that will always work to the extent that you are able to do the integral that you write down. So, Ampere's law is usually better for situations with nice symmetry that we'll see in a second. Second, you're going to find the direction of the magnetic field that you're trying to find from right-hand rule number 2. Then, we are going to choose our Ampere path. And we want to choose an Ampere path where the magnetic field is either constant or 0. And that will make our math easier in the future in a way we'll see in a second. Then the rest of the steps are fairly straightforward. We're going to calculate I enclosed. We are going to calculate the integral side of this equation, integral of b dot dl. And then we are going to solve for b. And the first example we're going to do is going to be a long straight wire. So let's have that wire carry current directly out of the page. So there's good symmetry here, so Ampere's law is a good choice. And we want to find the direction of the magnetic field from the right-hand rule. So we remember this. The magnetic field makes circles around the wire. And the magnetic field in this case will be making counterclockwise circles for this orientation. The magnetic field, we said, depends on the distance you are away from the wire. So for us to choose an Ampere's path with a constant value for the magnetic field, we want to pick a nice circular path with a consistent radius, so the strength of the magnetic field will be the same everywhere around this entire loop. And we'll go counterclockwise around this loop. So this is our path where we expect the magnetic field to be constant or 0. So, just want to note something. That the magnetic field could potentially have two components, a radial component acting straight out from the wire, and a tangential component that I'll call b theta, acting perpendicular to the connection to the wire, or tangent to our loop that we're going to go around here soon. Well, if we're taking b dot dl, well, at this location in our loop, our dl would be pointing directly to the left. So that means that br dot dl will equal 0. It also means that b theta dot dl is just going to be b theta times dl. So, one of the things we need to do is calculate our enclosed current. And in this problem, our enclosed current just equals, well, not 1, that's a lie, just equals I, the current we have labeled in the figure. So now we need to figure out how to find integral of b dot dl. Well, from what I wrote before, we can see that the only component that's going to matter is b theta. So this means the integral of b dot dl just becomes the integral of b theta times dl both scalars, excuse me. And we expect b theta to be constant. So we can pull it out front of this integral. And this is now something we can evaluate, even if we might not see it yet. So note that we have just the integral of dl. So we're going to add up tiny little bits of length as we go all the way around this closed path. So that integral here, with nothing else in the integrand except that dl, means we're just going to add up all of the bits of length until we reach the total. So what is the total length of this path that I've had? Well, it's just the circumference. So let's call that distance, the radius of this Ampere path, r. And this will just be 2 pi r. So now we can go back to step 6 to solve for b, to set these sides of these equations equal to each other. Because we have b theta times 2 pi r equals mu naught times our current enclosed. So we can then solve for our magnetic field as mu naught I over 2 pi r. And would you look at that? That's the same formula we got before. This is the magnetic field for a long, straight wire. And probably an easier way of determining the magnetic field for a long, straight wire than Biot-Savart law. So, real quickly, I wanted to do a couple examples that are shown in your book. For each of these situations, they want you to find the value of the integral of b dot dl. Well, we could do some horrible integral around those paths, but they haven't really given us much information here about the size or shape of those paths. So maybe there's another way to do this. And that way is that integral has to be equal to mu naught times I enclosed. So go ahead and see if you can work out these examples on your own here. Welcome back. We're going to do part A first, which is this one. So we have 4 different currents, a 2 amp current, a 5 amp current, a 3 amp current, and a 4 amp current that are all passing through the loop. Note that on the 4 amp current and the 2 amp current, this side of the current is not within the loop, so we don't need to worry about it. If we had a current that did something like this, it would kind of cancel itself out and we wouldn't need to worry about it. But we do need to pay attention to direction. So taking up to be positive, our enclosed current would be 2 amps going down, 5 amps going down, 3 amps going up, and 4 amps going up, which is 0. So that means the integral of b dot dl has to equal 0 in this problem. In part B, using the same conventions, the only current that actually passes through our loop is the 2 amp current, and it passes through the loop going downward. So in this case, our integral of b dot dl is going to be equal to negative 2 amps times mu naught. And last but not least, with part C, our enclosed current is, let's see, 7 amps going down, so we'll make that negative. 5 amps going down, so we will also make that negative. And 3 amps coming up out of the loop. We end up with negative 9 amps, so we can say the value of the integral b dot dl is equal to negative 9 amps. times mu naught. So the last thing I want to do here is one more example. And it's more of a real-life example. We want to find the magnetic field in a thick wire. Assuming thin wires is a lot like assuming a point charge or assuming no air resistance in projectile motion. It's not precisely true in the real world. So we want to figure out what is the magnetic field inside of a wire with actual thickness. So we can imagine ourselves a wire here that has some non-zero thickness. So we have this wire right here. And this wire is going to carry some current that I will label in pink. Sure, why not? Some total current, I naught, traveling upward. And the radius of this wire we will call A. So this is kind of a side view. I want to draw us a top view as well because it'll be helpful here in a second. We have the edges of the wire make a circle, and the current that is traveling towards us out of the board. And we have a radius of A for the entire wire. So, following our steps from before, there should be some nice symmetry here. And we're going to assume that the magnetic field direction is similar inside and outside the wire. That is, our magnetic field will make circles around the wire and within the wire, and those circles will be counterclockwise based on the way I have everything drawn. So, we want to find the value of integral of b dot dl and the value of mu naught times I enclosed for some sort of sample path that we could take through here for some Ampere loop. So I'm going to draw my loop in red again. And since we want to know the magnetic field within the wire, I'm going to draw my Ampere path here, actually on the inside of the wire. And this is going to be my Ampere path. So we need to evaluate the two sides of this equation. So integral of b dot dl, well, if we're assuming the magnetic field is in the same direction, well, let me use similar colors to what I did before. That would be to the left here, down here, and so on, basically following the direction of the Ampere path. So that means our integral of b dot dl, well, if b and dl are always in the same direction as each other, then this just simplifies to the integral of b times dl. And if the magnetic field has a constant value all along that Ampere path, we can pull it outside of the integral. And again, this part of the integral right here, we can evaluate. We're just adding up all of the little chunks of length. So, all the little chunks of length of this Ampere path put together will just be equal to the circumference of this Ampere path. So if we say it has a radius of little r, then that means 2 pi r is the integral of dl. So the integral of b dot dl simplifies to b times 2 pi r. Well, now we need to evaluate the other side of this integral. And our enclosed current here is not just I naught, because we're only looking at the current that is flowing within our loop here. All of the current passing through this outer section of the wire should not be included. So to find the enclosed current, we're going to take the total current and multiply it by the area of our ampere path divided by the area of the whole wire. So this is proportions, basically. The enclosed current divided by the total current is equal to the enclosed area divided by the total area. So this becomes I naught times, well, the area of the path is pi times r squared, and the area of the entire wire is pi times a squared. So this simplifies to I naught times r squared over a squared. Now we can set these equal to each other and solve. So we have I naught times r squared over a squared for mu naught I enclosed, well, put the mu naught out front, equals b times 2 pi r. So we can then solve for the magnetic field as mu naught I naught divided by 2 pi times the quantity r over a squared. And this is when r is less than or equal to the radius of the wire. Or our magnetic field, once we're outside the wire at a point, say, out here, for another ampere path, go ahead and do Ampere's law and verify this result for yourself, that you get mu naught I naught divided by 2 pi r for r values that are greater than or equal to a. So what this means is that the magnetic field of this wire behaves differently inside the wire versus outside the wire. So the strength of the magnetic field here inside the wire rises linearly in r within the wire up until you hit the edge of the wire. So here our magnetic field is proportional to r, and it rises up to a level that is equal to mu naught I naught divided by 2 pi r. But then, once we're past the edge of the wire and we're taking this larger ampere path around, we now have a 1 over r dependence to our magnetic field. So the magnetic field is proportional now to 1 over r. And will start to drop off at this point from that same connection point. So there will be a cusp here, but it will still at least be continuous. So sorry for the double videos today. I just wanted to get back on track with the syllabus schedule. The videos should be about 30 to 60 minutes going forward. I'm going to try to keep them on the short side, but you guys know me. So that's everything for today. Make sure that if you haven't already turned in the quiz, that you get that done and request an extension from me if need be, and continue to comment on Piazza and do the online homework problems. And don't hesitate to reach out to me to schedule a digital office hours appointment if you need it. All right, thanks for watching and have a good day.